Have you ever just, looked around and wondered about the stuff that makes up our world? I mean, from the crazy flexible screen on your phone to the high-tech fabric in your jacket, we're surrounded by these amazing engineered materials. But how do we actually make them?
Well, the answer in a whole lot of cases is polymers. Yep, these long chain molecules are pretty much the building blocks of modern life. They make up everything from plastics and paints to the most advanced textiles. So that brings us to the real question, right? How do scientists take these molecular chains and actually design them to have specific properties? How do you make one material tough enough for a car bumper, but another one conductive enough for a wearable sensor? The secret, it turns out, is all about scale. See, to build the materials of the future, you first have to understand them from the outside in, from how they feel in your hand, all the way down to their individual atoms. So you ready? Let's dive in.
First up, we're going to start at the big picture level. How a material behaves in bulk. How does it flow? How does it stretch? What does it do when you push or pull on it?
To do that, we have to enter the world of rheology. It's basically the science of how stuff flows. Just think about the difference between pouring a glass of water and trying to pour honey. That simple observation, that's rheology in action. It's all about how a material responds to force. And right away, this leads to a huge split in how fluids behave. You've got your simple or Newtonian fluids, like water. Their viscosity is constant. They flow the same way no matter how hard you stir them. But most polymers, they're non-Newtonian. Their viscosity actually changes with stress. Ketchup is the classic example, right? It's thick and stubborn in the bottle, but as soon as you shake it, it flows easily.
Now, a really common behavior for polymers is called shear thinning. When they're just sitting there, their long chains are like a tangled mess of spaghetti, which makes the material thick. But when you apply a force, like stirring it or spreading paint on a wall, those chains untangle, they line up with the flow, and suddenly it's way less viscous. This single property is absolutely critical for everything from getting smooth paint on a wall to high-resolution 3D printing.
Okay, so we get how the material flows. Now, let's zoom in, way in. Let's take a look at its surface. What kind of texture and, topography does it have at the microscopic level? To see this hidden world, our first tool is the Scanning Electron Microscope, or SEM. It works by shooting a focus beam of electrons over a sample. As those electrons hit the surface and bounce off, a detector gathers them up and builds this incredibly detailed, almost three-dimensional picture of all the tiny peaks and valleys. Now, it's super important not to get SEM mixed up with its cousin TEM because they do pretty much opposite things. SEM is all about the surface. It gives you those 3D-like images of the outside of the material. TEM, on the other hand, shoots electrons through an ultra-thin slice of the sample to show you the internal structure, kind of like a microscopic X-ray. So, two very different tools for two very different jobs. Okay, but what if we want to get an even more detailed look? For that, we can use atomic force microscopy, or AFM. And what's so wild about this is that instead of just looking, this technique actually feels the surface. It uses an impossibly sharp little probe on a tiny flexible arm to physically trace the landscape of the material. Honestly, the best way to picture it is like a tiny record player. The stylus moves across the vinyl, reading all the little bumps and grooves. AFM works just like that, but on a nanoscale, letting us map the surface with atomic precision. It lets us measure not just the shape, but also stuff like roughness and even friction. All right, we've seen the bulk flow, we've seen the surface texture. Now let's zoom in even further and decode the material's fundamental chemical identity. In other words, what is this stuff actually made of? For that job, we turn to something called FTIR spectroscopy. Basically, this technique works by shooting infrared light at a sample. The chemical bonds inside the material, like carbon-hydrogen or carbon-oxygen, are like tiny little tuning forks. Each one vibrates and absorbs a very specific frequency of light, which tells us exactly what kinds of bonds are in there. This whole process gives every molecule a totally unique absorption pattern. It's basically a molecular fingerprint. So by comparing this unique fingerprint to a huge library of known materials, we can figure out the exact chemical composition of our polymer. It's like a barcode scanner for molecules. A really common way to do this is called ATR-FTIR. As you can see here, instead of trying to pass light through the sample, the infrared beam first goes into a special crystal.
This creates this tiny little energy wave that kind of sticks out just beyond the crystal's surface. When you put your sample on top, it touches that wave and absorbs some of the energy. The light that's reflected back is now a little weaker, and that creates our molecular fingerprint. It's a really fast and powerful method.
But just knowing the chemical parts isn't always enough. We also need to know how they're all connected. For that, scientists use really advanced techniques like HSQ-NMR. It's pretty complex, but the result is this incredibly detailed map that shows the direct connections between atoms, like which exact hydrogen atom is attached to which exact carbon atom.
And this right here is the crucial difference. Think of it this way. FTIR tells you what chemical groups are in there. That's your parts list. But HSQ-NMR tells you exactly how those parts are pieced together. That's your assembly manual. When you put them together, you get a complete atomic blueprint of the molecule.
Okay, so we know how it flows, we know what its surface looks like, and we know exactly what it's made of. Now, for the really fun part, what can it do? Let's start uncovering the special properties and hidden talents of our polymer. First off, how does it react to heat? We find that out using something called differential scanning calorimetry, or DSC. This technique very carefully heats or cools a sample and precisely measures all the little energy changes that happen along the way. The result is a chart called a thermogram, and it reveals these critical temperature points. We can see the glass transition temperature, or TG, which is where a polymer goes from being hard and glassy to soft and rubbery. And for some polymers, we can also see the exact melting temperature, or TM. Knowing these numbers is absolutely essential for actually processing and using the material in the real world.
But what about its electrical talents? To figure that out, we can use electrochemical impedance spectroscopy, or EIS. It's a really powerful way to measure a material's electrical properties without damaging it. You just apply a tiny little electrical signal and measure the response. And from that, you can learn exactly how well it conducts or resists electricity.
And this is why it matters so much. By understanding a polymer's electrical side with EIS, scientists can engineer materials for some incredible technologies. We are talking about conductive fabrics for smart clothing, flexible electrodes for comfy ECG monitors, and even branding materials for storing energy. This is where material science gets really, really exciting. So let's bring this all back together. We've taken a journey from the big macro picture all the way down to the atomic level. By using this multi-scale approach, by combining rheology, microscopy, and spectroscopy, we get a complete holistic understanding of a material. We know how it'll behave, we know what it's made of, and we know what it's capable of. And having that complete picture is what lets scientists stop just analyzing materials and start truly designing them from the ground up. We have the tools now to see, to measure, and to manipulate matter with a precision that's just mind-boggling. We can literally design materials from the atom up to have exactly the properties we need. So the only real limit left is our own imagination. The question isn't, can we build it anymore? The question is, what will we build next?